Hello everybody. My name is Jakub Pingielski. I'm data scientist here at deepsense.ai. And today I would like to share with you some tips and tricks for semantic segmentation based on my experiences while participating in Kaggle competition. So let's see what's on the agenda for today. First, I will share with you some basic information about this competition. What were the rules? I will show you examples of data that was provided by the organizer. And I will also highlight some features of this competition that may make it interesting and practical, I think. After that, I will show you my baseline setup, my starting point for my experiments. After that, I will show you results of my training experiments. First, I will share with you experiments that succeeded, that actually improved my model performance. But after that, I will also share you some of my failed experiments, because I think it's also worth noting what actually works and what not, and maybe which aspects of modeling pipeline are not useful to tweak. After that, I will show you some tips and tricks, not from me, but from people that did better than me in this competition. And I'll try to compare and contrast some differences between approaches, mine and theirs. And after that, I have one slide with executive summary for you, just most important lessons learned from this competition. So let's start with some information about this competition. It was called HubMap plus HPA Hacking the Human Body. It was a semantic segmentation competition where we were given microscopic images of human organs. And the objective of this competition was to create binary masks and segment FTUs, which stands for functional tissue units. In a minute, I will show you some examples so you can know what those FTUs exactly are, at least visually. There were 5 organs in training and test data sets, but it was only one class segmentation. Organizers did not want us to try to predict what organ was on the picture, so the masks were binary. The evaluation metric was pretty standard for semantic segmentation. It was die score, which is also equivalent to calculating F1 score per pixel for each image. 2 technical details about this competition. We were allowed to submit only 5 submissions per day. So you have to think a little bit strategically about this competition. You were not able to, for instance, perform a grid search on multiple parameters and just submit hundreds and hundreds of slightly different models. The inference was made on Kaggle hardware, which was Nvidia T4 GPU, which had 16 gigabytes of RAM, which is decent, but you were not able to run the biggest models possible. So that it was a limitation. The maximum inference time for all testing images was 9 hours, and it was not a limitation at all. So you were able to create ensembles of multiple models. So these were the technical information about the competition. Here is a summary of my results. I managed to get 12th position out of almost 1,200 teams. Managed to get gold medal for my position. And my best model ensemble achieved 82% F1. And I lost about 1.5 percentage point to competition winner. And during this competition, I submitted over 200 different solutions and have run over 500 experiments. And based on that, I think I have pretty good ideas what works and what does not work in this kind of competitions and projects. Let's talk a little bit about data. There were actually 3 different data sets. First was training data set that was provided by organizers. It consisted of over 300 images that all came from HP database. It's a medical images database. And those images were quite large. The resolution was 3000 by 3000 pixels. Then there were also images in public leaderboard. So we were not able to see those images, but our models were evaluated on the dataset during the competition. And this dataset was a mix of images from HPA and also a different dataset, which is called HUMAP. And in a minute, I will show you differences between those 2 datasets. And what's interesting is the resolution of those images were spanning from very small to very big, so from 160 to up to 4,500 width. And finally, our model was evaluated after the deadline of the competition on private leaderboard dataset, which consisted only on HUMAP images. So I think it was an interesting setup where you had to train on one dataset, your model, but you need to train it in such a way that it will perform good on quite different dataset. And I think it mimics quite well our usual business cases in commercial products. So here are some examples of dataset provided. Here are 2, on the left-hand side, 2 images of spleen, and on the right-hand side, those images with the binary masks. So you can see where the FTUs are. One thing to notice is that, well, colors are quite different, right? Even though it's still a spleen, there are purple and brown images, and it's not very easy to notice where those FTUs should be located. If you look close enough, there are some darker blobs on those images, but here on the kin images, those FTUs are not darker blobs, but blobs with like a white edge around them. And again, there are quite striking differences in color between images in the same organ. Here we can see images of lung, which was the most difficult organ to find FTUs. And many people on the competition forum said that the quality of annotations for lung was pretty bad. And they claimed that some of the annotations were very dubious or even wrong. So again, I think it's very similar to some of the real-world problems that you face on your day-to-day work. Here's another example of large intestine images. As you can see, there are many more FTUs than on the previous images. And again, there are some darker blobs in those FTUs. So here we have a comparison of images from those 2 different data sets. So as you can see, the colors are quite different, and all the images from HPA dataset were circles with a white background, whilst images from HubMap dataset were filled squares. So here we have a problem where we need to try to train a model so it will work on quite a different domain. And to sum up, there was a big difference between training and test datasets. There was also a pretty big variability between intra-class and inter-class images in color, size, and quantity. And regarding especially lungs, some of the annotations were inconsistent or even dubious. So that was information about dataset. Now let's talk about my baseline model for this competition. So first I started by resizing images from 3000 pixels to 512. It was a good starting point for rapid prototyping, but eventually I switched to bigger images to 2024. I also started with quite small models based on convolutional neural networks. Namely, I started with EfficientNet before as encoder and unit as decoder, and I think it's a pretty strong baseline for semantic segmentation, at least for now. Some more technical details regarding training procedure. I used constant learning rate, an optimizer, and I used binary cross entropy for loss function. I based my code on library called segmentation models PyTorch, which I highly recommend since it has implemented many different architectures with weights. For validation, I used 5-fold cross-validation with certification for organ types. So in each fold, there were similar. There were images from each organ in certain aspect. And since I was performing hundreds and hundreds of experiments, I needed a tool to manage those experiments, and I used Neptune, and I also highly recommend that tool. So that was my startup point. Let's see what worked in this competition. I think the most important aspect in this competition was applying very strong data augmentations for training images. So I used augmentation library, and I had 2 core augmentations that I applied to every image during training. And I did so to adapt those HP images to HubeMap domain. And those augmentations were RGB shift and hue saturation value. And I also added some different augmentations, and I divided them into different sections, for instance, position augmentations or deformation augmentations. For each section, I tried different probabilities of applying augmentations from given section during training, but I find out that the best augmentation, the best probability for each different section was 99%, so very high. And it's worth noting, I think, that there was no chance of my model to see an augmented image during training. And overall, I use 19 different augmentations in my model pipeline, and I think it's significantly stronger than your default ones. I was worried that my model will not be able to train with such strong augmentations, but it turned out that it worked quite well. On this slide, we can see an example of these augmentations. So I created 9 random augmentations from the image of the left, and as you can see, the colors are quite different. So that's because of very strong RGB shift. You can see also some black rectangulars, and that's an augmentation called a dropout, and I think in other places you can know it by cutout. Another thing that really worked for me in this competition was switching from convolutional neural networks to models based on transformer architecture. At first, I was hesitant on using transformers in this competition since I believed in some common misconceptions about transformers, and here I have listed some of them. So I thought that transformers are best suited for problems from natural language processing domain, not for computer vision. And they are very big, they are very slow and hard to train and inference, and they require lots and lots of data. But it turned out that nowadays these statements are all false. And you can find very optimized, very small transformers for vision. There are different architectures, and I have listed 3 of them that are currently state-of-the-art. And they are middle-sized, so you can use them in your project if you want to. So these are CodeNet, which I have used extensively in my experiments, but there's also something called Code and Pyramid Vision Transformer version 2. So if you're wondering what vision transformer you want to use in your project in 2022, I would recommend those 3 different architectures. Yet another thing that helped me during this competition was applying test time augmentations, TTA. What I did was for each test image during the inference stage, I created additional 7 versions of test image by applying different rotations and transposition for image. And after that, I performed inference for those all images and I averaged the predictions. The good thing is that you can use a library called PyTorch Toolbelt. And if you use that library, you just need to change one line of code in your inference pipeline to apply all those transformations. So that's neat. Another thing that worked in this competition and improved my model performance a little bit was applying state normalization, which is kind of color transfer between 2 images. And what I did was I only applied state normalization during inference. For each test image, I selected randomly an image from training dataset from the same organ. I applied state normalization. I repeated it 2 or 3 times for each image. And again, I averaged the predictions of different state normalized images. And for that, I use Stain Tools library, which I also recommend. And here we can see what it looked like in practice. So for each test image, I selected 3 different training images from the same organ. As you can see, they have quite different colors. So after applying state normalization, we have 3 different normalized images, and we can use them during the inference. We'll get quite different predictions, and we can average those predictions and squeeze a little bit more performance from our model. And I think it worked pretty good in this competition because we had different colors in training and test images, and it helped to apply this procedure. Another thing that helped in this competition was tweaking decision thresholds for each organ. So by default, for all organs, if our model predicts there's a probability higher than 50% for each pixel, then we selected this pixel as FTU, but it turned out that lowering those probabilities for different organs improved the performance quite a bit, especially for lung, that the threshold was only 10%. And I think it was because those annotations for lung images were quite difficult. Now our model was not able to predict properly those lungs, so we need to lower our threshold significantly. And final trick that helped in this competition, which is very popular in all other competitions on Kaggle, is using model ensemble. So I have used a simple averaging of predictions from different models. I have used 5 different models. In all of them, I used code like medium architecture as encoder and used different decoders, either unit or the former. And I've used models trained on different folds. So I have created 5 folds, but I've only used models trained on 2 different folds because it turned out that creating bigger ensemble with models from all 5 folds decreased the performance, and I suspect that it was because some folds were better than other, mostly because in some training folds there were those bad annotations from Lang. So these were all experiments that worked for me. Let's see what did not work in this competition. I tried different optimizers. This competition, I've stick with your basic Adam optimizer, but I've tried some different versions of that. So Adam W or RAdam. I also tried some more exotic optimizers such as Look Ahead or Ranger 21. It turned out that the performance was almost the same or even worse for all of those optimizers. Also, different learning rate schedulers such as Reduce on Plateau didn't help. I tried different loss functions, Lovash loss or focal loss, which is also pretty popular in semantic segmentation competitions, did not improve my models. Many people in Kaggle recommended using stochastic weight averaging, so selecting different checkpoints during your training run and average weights of your model. From those checkpoints, it sometimes helped, sometimes not. So I didn't use it finally in my ensemble. And since the images provided were quite large, so I also tried tiling those images, so creating a grid of smaller images out of those huge images and train my model on those smaller images. Also did not improve my model performance. And final thing that I tried and failed was instead of predicting binary masks, I tried to predict multi-class masks for each organ, and also did not improve my my model. And I think lesson learned here is that there are many things that you can tweak during your training procedure, and there's no free lunch. You have to try multiple things and see what works and what not. But for me, those things were not that important. Now let's see what other people did differently than me. So I checked people from top 10, and most of them have written their solutions for this competition. Some of them even provided code, and most of the teams that performed better than me have added external images to the training dataset. They find images from HPA and HubMap on the internet, and they used pseudo labeling for creating labels for them. So when they had a pretty decent model, they used those model predictions as ground truth labels for those external images, and they have added them to training data set, and it improved their performance. And some teams have either removed some problematic images, especially from Langs, or just hand labeled them, and trying to find some better annotations for them, and also improved those models with those different annotations. Another thing that some people did differently than me was using different models. So especially most teams use larger ensembles than mine and use more diverse set of models. So I've used only 5 models, and they all had models based on transformers. But here most people use a mix of convnets and transformers. And here I have listed some architectures for you to try that were popular amongst many teams. So for encoders, EfficientNet with its many variants is very popular. And for decoders, DeepLab and UNet++ architecture is also quite useful. One last thing to say about modeling is that one team tried to train model to predict not only binary masks, but also predict organ and pixel size of the images, which was metadata. And they claimed that it improved the robustness of their model, but adding auxiliary loss from those additional model outputs, which is an interesting trick to try. And one last aspect of this competition that other teams did differently was different training. So I have used resolution of 2024 for all of my models, but many teams tried different resolutions and created huge ensembles of models trained on different sized images. I've mentioned that different optimizer did not help me, but it turned out that for some people it worked, especially AdamW and RAdam optimizers were popular. Also, for me, cross-entropy was the best, but many teams tried weighted loss, so they added to cross-entropy some different losses such as Lovash loss and Tversky or Jacquard loss. So it's also worth trying. Some teams tried augmentation called cut mix, which is just basically cutting a part of one image and pasting it to another, and they claimed it improved their performance. Regarding learning rate schedulers, cosine decay with warm-up was quite popular. Some teams tried state normalization, but in a different way than mine. Namely, they applied it to all training data set, not only during the inference, as I did. And many teams claim that using stochastic weight averaging or just plain simple averaging a couple of best checkpoints from your models helped improving the performance. So as you can see, there are some differences between what worked for other teams and what worked for me. And I guess, again, there's no free lunch. There's no one final recipe to train segmentation models, and there are just some intuitions that you can have, some things that worked in past projects, and you need to try as many as you can and see what works and what not. But hopefully I have given you some general tips what you should focus on. And here is promised executive summary for you, the most important tips from this competition. So first of all, you should, in my opinion, start with models based on convolutional neural networks. I would recommend EfficientNet family as encoder and UNet as decoder, and it should be a pretty strong baseline. After that, if you have time, you might want to try transformer-based models, because there are already some pretty decent and medium-sized models that perform better than ConvNets. I would also recommend using stronger than usual data augmentations, especially if you if you suspect that there will be a domain shift between your training data set and your production data. If you have unlabeled data, you might want to try pseudo labeling if you have already pretty decent model, and use those images in training data set. If there are some images that are very hard to make predictions on, you might want to double check them or even relabel, because there might be some mistakes in annotations. And my final recommendation is that if there is no strict limit to inference speed of your final solution, if your model does not have to work in real time, you might want to try test time augmentations and ensembling different models to squeeze some performance from your model. So that's all tips and tricks for me for today. Thank you, everybody, and hopefully my tips and tricks will be useful for you in your projects. Thank you, and see ya.